Hello, everyone. Welcome to our talk. I'm Wen. I'm super happy to be here with my colleague, Chien-Chin and Natalia, to present you PyTorch Symmetric Memory, a new way of doing distributed programming. We have plenty of time, so let's start with a couple polls. Do you think it's possible to program your system as a single gigantic GPU? Can you raise your hand if you believe that's possible? Can you raise your hand if you think that's not possible? OK. Second poll, this is how we write our distributed program today. Everything on the host side, we call some torch ops, and then we call dist.reduce to do the communication. Do you believe one day we can move all this code into a device kernel and let it run inside a single device kernel and let it do communication? Again, can you raise your hand if you believe that's possible? OK, we have more people now. Can you raise your hand if you think that's not possible? Great. So if you have the same imagination as we do, I hope you'll find the next 25 minutes worth your time, because we're going to bring you a one-stop shop for authoring your own multi-GPU kernel. So what is symmetric memory in PyTorch? We can go back to the two basic communication mechanisms between processes. One way is called message passing. It is similar to packing all the information into a box, take the box to a post office, and ask the post office to ship it out for you. And because of the round trip to the post office, you will want to pack as much information as possible into the box. Right? And hence, this limits your flexibility of communication. Shared memory is another way, where two processes just open up some of its own memory space to be visible to the other process. And the communication, the data access can be made arbitrarily at a very fine grain. So if it is that great, how should PyTorch enable it? Next welcome Natalia to walk through it.
Hey, so let me tell you a little bit more how PyTorch enables symmetric memory on the technical level. Did we have a slide in between?
Sorry.
So there should have been the slide that's. We need to correctly allocate this memory on all the GPUs that can be used for inter-process communication. But unfortunately, correctly allocating it requires some less common knowledge. It uses APIs from different vendors that are not particularly well documented. And it's really easy to go haywire trying to do this. In fact, even when we were doing this, we fixed the memory leak pretty late in the game. And it was present for a long time, because it's hard to know which APIs to call in which order. Then enabling peer memory access is also kind of tedious. So if you are left needing to do it yourself every time you want to experiment with some distributed APIs, this would create quite a lot of developer friction for you. And finally, even if you opened up those memory regions for the process to communicate, it still doesn't mean that any process can barge in and write in any address space at any moment it wants. They need to agree between themselves when a particular memory is safe to write to, when it's safe to read from. Are all the reads and writes visible the way we expect them to be visible? Memory spaces in GPUs are a complicated topic, and getting it correctly is hard. So PyTorch Symmetric Memory is solving all those problems for you. And the way it's solving those problems is you are partitioning the address space in each of your devices. You designate some areas of that address space as accessible to all your peers, allocated as a symmetric memory. And from then on, you can write your own communication kernels or implement whatever communication patterns that you want to implement. The agenda of our today's talk is a simple example of how you can use existing kernels and existing PyTorch symmetric memory. Then we'll move on to how you can write your own kernels with symmetric memory. And finally, we'll touch upon going to a larger scale than just intranode or NVLink domain. Simple example of using symmetric memory in PyTorch, you are allocating symmetric memory in a very similar way like you would allocate any other tensor in PyTorch. Then you call a rendezvous on this tensor to make sure that all your peers know how to communicate with this region in your memory. And from then on, you can use it in your kernel or in other communication patterns. The simple way to do it is, for example, to call the symmetric memory kernels that we already have implemented in PyTorch, like one-shot all reduce. If you want to do something more complicated, an example on the right shows you the very bare minimum of what you can use to write your own kernels. You are getting pointers to your peer devices that you can use for communication. Typically, you would start this kernel with synchronizing and making sure that all the participants are ready to start and the memory is ready. And you would do the same thing in the end, because otherwise your kernels might get out of sync. But in the middle, it's just the regular CUDA code that you would otherwise be writing. And here we are showing the results for the one-shot symmetric memory kernel mentioned on the previous page. And in latency-bound regimes where you are all reducing small messages, the latency of this direct memory access kernel is clearly much better than what Nickel or the two-shot implementation provides. So what capabilities does symmetric memory unlock? It allows you to implement arbitrary communication patterns. For example, if you want only a subset of your devices to participate in some collective communication, that's pretty hard to do today with Nickel. But with symmetric memory, you just write your own kernel that calls only those peers that you want without creating a new process group. And it will work because you, as a developer, control it. It enables, as Kaya mentioned in the beginning, computation fusion within a single kernel. And apparently, a lot of you guys are already doing it, but we are just hoping to make this experimentation easier and more accessible to everyone. And finally, it enables low latency remote access, so in latency-bound regimes where you just want to access your peer memory as fast as possible, this is your ticket. And next, Kai will talk about some custom communication patterns that are enabled by symmetric memory.
Thank you, Natalia. For arbitrary communication patterns, I'm going to give two examples today. One is called a mixture of aspers, and second is tiled tensors communication. Mixture of asper is an architecture that shuffles token between the attention layer and the asper layers. And the key part of it is that there is a router that runs on each GPU to determine which token goes to which asper. And because of the decision is dynamically made, we are faced with an issue that when we look at the input buffer to the all-to-all shuffle, the split of the asper chunks are dynamic determined, and the information lives on the GPU. So if we were to use a traditional Nickel API to perform this all-to-all, one issue would be that we will have to sync the split decision back to host, and then wait for the host to issue the next GPU operation, which is all-to-all. And because of this host-to-device sync, the GPU will be waiting for more instructions to do, and hence a store in the GPU timeline, as you can see here. And that hurts the performance. With symmetric memory, everything can be inside the kernel, as Natalia just mentioned. On the left-hand side is a device function that does the split exchange. Here, I'm telling my peer, hey, how much data I want to send to you. And also, I'm telling my peer, hey, this is the offset in my send buffer that you should get the data from. And on the right-hand side is another device function that my peer read those meta information and use that meta information to perform the actual data fetch from my symmetric memory buffer. So with this, we avoid D to H sync. And what's the speed up? 4x if we want particularly inference workloads. If you look at the trace, you can see that we totally eliminate the gap on the GPU side. And every kernel, no matter it's compute or communication, they got packed up together. And because of the no-sync computation, we can apply CUDA graph, which is really a key for how you run your DR application fast. The second example is from tiling. Here is a big tensor. Every rank has this tensor, just with different data. And I'm cutting the tensor into 4 quadratures. And I want to reduce each quadrature to a different rank to perform some data processing there, so that I can parallelize the data processing on this big tensor as a whole. This is a very common pattern in high-order optimizers that does block-wise optimization, because you want a different rank to optimize different part of the parameter. And with traditional APIs like Nickel, this is not possible because Nickel cannot support memory that's non-contiguous. And a tile is exactly a data layout that's non-contiguous. But with symmetric memory, we can easily control where the CUDA thread should go look for the data. We can tell, hey, this is the starting point of a contiguous row, and that is the ending point of a contiguous row. So with that, you can write your own communication kernel, and that's what we do in PyTorch Symmetric Memory package. We surface a op called multi-root tile reduce. So you just need to provide a bunch of tiles like this one, 4 tiles, and then specify a bunch of roots, 1, 2, 3, 4, corresponding to each tile. And then the op will end up as output tile at each of the rank. So these are just some examples of we doing things, but we want you to be the painter of the picture. Next, my colleague Chien-Chin will tell you how you can write your own kernel easily.
Thank you, Kerr. So Natalia and Kerr already discussed how powerful symmetric memory is, and also show us some interesting communication kernel. So you might want to write your own communication kernel. So how can you do that? So Triton is a very popular Python DSL developed by OpenAI for writing GPU kernel or like a kernel for other backends. So can you use Triton with symmetric memory? Sure, you can. This slide shows a communication skeleton written in Triton. And the input to this Triton kernel are symmetric memory buffers, signal pad, and also local data. We first use Triton's load and store to load the data and put it into symmetric memory buffer, which will be then accessible by the remote rack. Then we use load instruction to load from remote rack's buffer. Then you can do whatever you want, whatever computation you want with this loaded data. All of this can be done with native Triton primitive. But as Natalia mentioned, we need some synchronization. How do we know if the remote buffer is ready or not? So this is the part that requires some low-level PTX implementation, which we wrap inside an API that you can all use. So with this skeleton in mind, let's see how we can actually apply Triton and a symmetric memory to a real use case. So this code snippet extracted from a real model. And it first perform O-reduce, and then add a bias to the result, and finally perform RMS node. A pretty simple function. So when we use this model for inference, the input can be as small as 10 kilobytes. So this poses several issues. First, nickel O-reduce is not designed for low latency use case. And also because the input is so small, the 3 kernel launch overhead can be a problem. So let's see how we can use Triton and a symmetric memory to solve both issues. So for the first low latency issue, there's a well-known O-reduce algorithm, one-shot O-reduce. The algorithm is pretty simple. It's just like each rank receives the data directly from all other rank and perform the reduction locally. So we actually implement the core logic of this algorithm on the right side. There are 2 loops. The outer loop just iterates through all the data block. And the inner loop iterates through all the ranks, whether it's local rank or remote rank. And we calculate the data address of each block on each rank. And again, we use load instruction to load the data, whether it's local data or remote data. It's the same. And we load this data and perform the computation, which is the reduction. And we finish the one-shot O-reduce implementation. So we solved the first issue. How about the second issue, the kernel launch overhead? Can we extend this implementation? That's what we are going to do. So on the left side, this is our final implementation. On the left side, we simply just extend our for loop to include the bias addition, because bias addition and also reduction, they are all element-wise operations, so they can easily be put into the same for loop. On the right side, we have RMS node implementation in Triton. And we put all of them in the same kernel, so we only have 1 kernel launch. So finally, we also implement like 2-shot O-reduce, and we experiment on H100 machines. And we can see that for small input size, our symmetric memory implementation actually outperforms twice faster than nickel communication. And when we increase the input size, the gap becomes smaller. And eventually, yes, we need to switch back to nickel's implementation. But this showcases a very important use case of symmetric memory, which allows you to write your own custom communication kernel to address some issues that the traditional communication library doesn't cover. And we put all of these APIs and also fuse kernel at Triton. And if you are interested, there are many more interesting kernels at the Triton kernel. And you can stop by Triton's poster this afternoon. Next, Ke is going to discuss how to scale out symmetric memory.
Thank you, Chien-Chin. Yeah, we really don't want to stop there. So we want your kernel to be even able to go across node access memory. How do we do that? Let's look at how the traditional way works. It actually is a 3-party game. First, the GPU will have to prepare the data and signal the CPU that the data is ready. And then the CPU as a helper would prepare metadata for the network transaction and ring the doorbell at the NIC. Lastly, the NIC will fetch data from GPU and send it out. So this 3-step round trip has a lot of overhead and hurts the performance of the network access. But we want to let GPUs instead of CPUs talk. How do we do that? NVIDIA have this great library called IBGDA, which essentially allows GPU to directly initialize network transaction with the NIC. And thus, it has much shorter initialization time. Also, as we know, CUDA block has many threads. so that we can prepare all the messages together concurrently and have massive amount of threads pumping messages into the network pipe. This helps improve the ramp up of the network bandwidth. And lastly, RDMA is the core mechanism that allows the NIC to access the memory space of a remote node. Just now, Chien-Chin told you how we can program symmetric memory with Triton. So how can we let Triton go across node as well? This is how. Triton calling enrichment plugin. You just write your regular Triton kernel with triton.jit. And inside the kernel, you can call enrichment functionalities in a Pythonic way. Enrichment.put, send some data to some destination. And the Pythonic API even observe tensor semantic, where you don't actually need to give number of bytes. You can just give number of elements as how you operate a tensor. And for Triton to recognize that this is an external plugin, it's very simple with Torch. You just need to add this requires enrichment decorator. And Triton will bring in the assembly when it compiles the code from both the kernel itself as well as the enrichment library. On the host side, just regular business, allocate the symmetric tensor, rendezvous it, and then call the Triton kernel with the symmetric tensor. This allows the kernel to go across node. So what will happen in the future? Natalia?
Yeah, so we are not going to stop here, and we will work on both including new interesting operations in PyTorch itself, and we hope that you as a community will use symmetric memory to realize some of your developer plans. We also want symmetric memory to be actively used in our DSLs, such as Triton and Helion, and people are already actively working on using symmetric memory in Helion. Again, some of the details can be seen in the Kraken poster today. And finally, we want to do better fault localization and reporting. Unfortunately, I'm out of time here. So the main takeaway I want you to have from this talk is that you shouldn't be afraid of actually writing your own communication kernel. Similarly to how Triton recently enabled a lot of people who are not expert CUDA programmers to write their CUDA kernels, you should be able to write your communication kernels also without doing a lot of extra prep work. And thanks to our awesome colleagues who worked on this project.
We're ready for questions, if there's any. I think Pavel?
What is your recommendation? How can we deploy performance issues with this library, with symmetric memory? I can explain.
Oh, there's a mic coming. Sorry.
Thank you. Hi. What is your recommendation? How can we debug performance issues, communication issues with symmetric memory when we use symmetric memory? I can explain. When we use PyTorch, we can use, for instance, PyTorch profiler and see clear nickel calls and see how long it would take. With this library, as I can see on your slides, there is a kernel that combines computation and communication, and it takes some time. And it also, as you said, heavily depends on the hardware, on the NIC, on the on GDA in general, on GPU direct async, and the following. So how, if it takes, for some reason, if it takes a long time, how we can debug this issue and how to, who we should complain to about the performance of symmetric memory on different hardware.
Do you want to take this?
Kai, do you want me to take it, or do you want to answer?
Yeah.
So the first thing with all communication kernels is to determine if it's a really kernel issue or if you are just facing some straggler in your workload. And you can use PyTorch profiler to help you do that. After you've determined that, yes, actually there is no straggler, it's a kernel taking a long time, if you are using Triton, Triton provides profiling tools that allow you to mark the regions of the kernel, and they would tell you, for example, in their profiling tools, how long the computation part of the kernel takes place and how long the communication takes place. And if you've localized your failure to communication that's not getting as much bandwidth as you would expect, then at this point, since we are relying on NVSHMEM, I would talk to NVSHMEM people about what's going on.
And I think that would be a great question for NVIDIA too. How can you look inside a kernel to see what the instructions is doing? Maybe inside compute have some kind of functionality like that? Second question, sorry. Oh. I think the mic is at the back. Sorry.
So I'm new to NVSHMEM. I've seen the put and get constructs in your slides. Are they blocking constructs?
That's a great question. There are both blocking version, which is just put or get, and there's a non-blocking version, which is put MBI and get MBI.
OK. So in the non-blocking version, how do you manage the synchronization?
So you must pair it with enrichment.acquire call to make sure the transaction finish.
So would they be similar to acquire lock sort of a thing in the glue-on TLX level, or the synchronization primitives even very higher level? So what is the level of synchronization primitives in the NVSHMEM? I think that's the question.
Not familiar with glue-on, so sorry.
Offline.
Yeah.
Last one.
Oh, hi, Sean McGovern from Red Hat. I just had a question in the off-node context. So if we're thinking of this partition global address space as kind of a flat thing, how do we think about data locality and what sort of challenges might there be?
Another great question. So I hope you're only exchanging data you need to exchange. Yeah, there are a lot of way of preserving data locality, right? So for example, pipelining, you put the entire model weight on one single GPU. That's one way of preserving data locality. And so yeah, it's actually the programmer's own wisdom rather than a burden of this programming model.
Thank you.